Engineers spent about $100 million to stop this building from sinking. The monitoring data says they made the lean worse. How does that happen? In 2021, drilling crews were working the streets around a 58-story residential tower in downtown San Francisco. The repair had been running for months. Then the numbers came in, and the building was moving the wrong way, not stabilizing, leaning faster than it had before anyone touched it. The tower at 301 Mission Street opened in 2009. 58 floors of reinforced concrete rising above the financial district, one of the tallest residential buildings in San Francisco at the time. From the outside, it looked like exactly what it was supposed to be, a high-rise that worked. The original foundation design did not promise zero movement. The city's 2017 structural safety review records that engineers anticipated about 1 inch of settlement by the time construction finished, and about 5 inches over roughly 60 years. Those were the numbers the design was built around. What the building actually delivered was something else entirely. By July 2017, the tower had already settled about 17 inches. Most of that movement happened after the superstructure finished in 2008. The top of the building stood about 14 inches off vertical to the west and about 6 inches to the north, a measured northwest lean. The tower had blown past its 60-year settlement expectation while it was still young, still moving at roughly 1 inch per year after 2010. No collapse occurred. Residents were not evacuated. The building remained occupied throughout. But the numbers on the monitoring record told a story that demanded an explanation, and the explanation starts underground. The foundation beneath this tower rests on a 10-foot thick concrete pile cap carried by approximately 950 precast concrete piles, each about 80 feet long. Those piles drive down through the fill and bay mud near the surface and terminate in dense marine deposits, a sand-like soil layer that sits well above the deep bedrock. The rock lies much, much deeper. These piles never reached it. That gap between the pile tips and the rock is the mechanical center of this case. Below the dense marine deposits where the piles stop sits a layer the engineering record calls the Old Bay clay. This clay is soft, compressible, and saturated with water. When a very heavy structure presses down from above, even a pile-supported foundation still transmits stress into the soil beneath the pile tips. The piles carry load into the dense layer, but the load keeps pressing down into whatever sits below that layer. And what sits below is clay that compresses slowly over years, under sustained stress. The city's 2017 safety review reached a finding that seems counterintuitive at first. The piles had not failed. The piles were doing exactly what they were designed to do. The movement was happening in the Old Bay clay beneath the pile tips, not because the piles had lost their load-carrying ability. The soil below them was the problem, not the piles themselves. Pre-construction surveys had identified this compressible clay. The layer was on the record before the first pile was driven. The design proceeded with a foundation that stopped above it. As the building's weight pressed down for years, that clay began a slow, two-part compression process that would not stop quickly. The settlement was not driven by the tower's weight alone. Peer-reviewed analyses connect the movement to the building's self-weight combined with temporary stress increases from repeated dewatering at the tower site and at adjacent construction sites between 2006 and 2018. The major transit center excavation next door drew down groundwater repeatedly during that period. Dewatering lowers the water pressure in saturated soil, which increases the effective stress on the soil skeleton, which drives compression. The asymmetry that produced the northwest lean, rather than straight-down sinking, connects to that time-varying dewatering and three-dimensional excavation effects on one side of the building more than the other. How responsibility splits between the original foundation design and the neighboring excavation and dewatering is disputed and unresolved. The peer-reviewed record acknowledges that lateral movement from adjacent excavation is a three-dimensional effect that one-dimensional settlement analyses cannot fully capture. No single engineering body has issued a final, apportioned finding on that question. Settlement tracking ran from construction onward. By the time the city's 2017 review was published, the documented lean stood at 14 inches west and 6 inches north at the roof. The review concluded the tower's resistance to major earthquake shaking had not been appreciably compromised at that point. This was a failure of foundation performance and serviceability, not a collapse risk. But the movement had not stabilized, and the review called for continued monitoring. By June 2019, the Homeowner Association's monitoring record put total settlement at about 17.3 inches, greatest near the Mission and Fremont Street corner. The roof of the tower tilted about 15.5 inches to the northwest. That northwest corner was the same side that would later become the focus of the repair effort. By 2019, a repair concept had been approved. Add new rock-bearing piles along the building's north and west sides, tie them into an extension of the existing foundation mat, and use those new piles to transfer load from the compressible clay all the way down to bedrock. The idea was to give the building the foundation it never had, at least on the side that had moved the most. The 2019 engineering design review that approved the concept carried an explicit warning. Because of the old bay clay's behavior, stress changes from the new piles could keep developing for months, even years after the piles were installed. The review required intensive monitoring during construction and for a decade afterward. The engineers who approved the plan already understood they were acting on a stress-sensitive clay system, not a rigid one. The clay would respond to disturbance. The question was how much and when. The city's planning record described the concept as approximately 52 perimeter piles drilled to rock. The number and arrangement were governed largely by site constraints and by how much load the existing structure could physically transfer, not by an idealized performance target. The precise revised pile count after the later pause is not stated in the verified public record, and this account does not assert one. Production work began in May 2021. Large diameter casing and rock socket drilling started along the north and west sides of the building, the margin showing the greatest movement. The plan was to establish rock-bearing support on that side before completing the rest of the perimeter. Sensors tracked both vertical settlement and horizontal deflection throughout, feeding data into the official monitoring record in near real time. Within months, that data delivered an unexpected result. By the August 2021 pause, the building had gained roughly 5 to 6 inches of additional westward roof deflection and about 2 inches more to the north. That was more movement in a few months of repair work than the building had recorded in years before the crews arrived. The casing work on Mission Street stopped on August 2nd. The Fremont Street rock socket work stopped on August 22nd. By September 2021, the city disclosed to bond investors that the approximately $100 million retrofit had been paused because monitoring showed settlement rates may have increased as a result of the retrofit construction itself. The clearest pattern in the engineering record is temporal. The extra movement tracked the construction operations directly. The official monitoring showed that since the May 2021 start, added settlement was not uniform across the building. The northwest side recorded about 2.0 to 2.4 inches of added settlement. The east side recorded about 0.6 to 1.0 inch. That differential is the mechanism. One side of a rigid structure dropping faster than the other does not produce straight-down sinking. It produces rotation. The drilling, casing installation, rock socket work, and the groundwater and stress perturbations that accompany that kind of work disturbed the same stress-sensitive clay the repair was designed to escape. The disturbance arrived before the benefit. The new piles transfer load onto rock only once they are installed and loaded. During the installation window, the clay on the northwest margin experienced additional stress changes and compressed further, while the opposite side moved comparatively little. The repair produced its harm before it could produce its help. The engineering record does not reduce this to a single cause. Vibration alone is not the stated culprit. One neighboring project alone is not the stated culprit. The record points to the combination of construction-related disturbance acting on a clay layer already primed for compression on the side of the building already carrying the greatest accumulated movement. Whether the tilt acceleration during the 2021 installation window fell within or outside the project's modeled tolerance is disputed. The project's engineers characterized the movement as within transition period expectations. That characterization has not been resolved by any independent public inquiry. What followed the pause is best understood not as a clean redesign, but as a staged, instrumented restart. The January 2023 monitoring report records a first-stage load transfer in which 6 specific piles were loaded to 500 kips in 100 kip increments, with the foundation mat extension moving only hundredths of an inch per step. That is a fundamentally different operational approach from the original installation phase. Slower, smaller, measured at every increment. By early 2023, total settlement stood at roughly 18 to 19 inches. Roof deflection measured about 26 to 27 inches west and about 11 to 12 inches north. Those numbers are worse than the day the repair began, but the rate of movement had been brought down from the peak recorded during the 2021 installation window. The physics underneath all of this is not exotic. The Old Bay clay behaves under sustained load the way a saturated sponge behaves under steady pressure. Water is slowly expelled, the clay skeleton compacts, and the surface above drops. This process began the moment the building's weight was applied during construction in 2006 and did not stop quickly. The compression runs in 2 phases. First, volumetric strain as added effective stress drives water out of the clay pores. Then secondary compression, a slower, time-dependent creep that depends on the clay's stress history and continues long after the first phase slows. Peer-reviewed analyses treat both phases as the dominant mechanisms of settlement at this site, not as secondary effects. The piles transmitted the building's load into the dense marine deposits as designed, but the stress field below the pile tips still reached into the Old Bay clay. That deep clay compressed far more than original projections assumed, and it compressed unevenly because the dewatering and excavation effects were not uniform around the building's perimeter. Uneven compression in a deep clay layer beneath a rigid high-rise structure expresses itself as tilt. The building did not just sink, it rotated toward the corner where the clay compressed most. This case does not reduce to a single engineering failure. The record points to a combination: a foundation that terminated above a deep, compressible clay layer, tower self-weight, and repeated dewatering driving that clay far past its projected compression, asymmetric groundwater and excavation effects producing the northwest lean, and a repair whose construction process disturbed the same sensitive clay before its load transfer benefit could take hold. No independent engineering board has issued a public root cause determination apportioning weight among those factors. The most pointed findings in the public record come from litigation-commissioned work, produced for adversarial purposes. The city's 2017 review found that the tower's resistance to major earthquake shaking had not been appreciably compromised. The city has not issued an unsafe structure notice. This is a serviceability failure, a building that leans, not a building approaching structural collapse. San Francisco responded to what this case exposed by tightening the front end of the problem. By June 15, 2020, the city had adopted Administrative Bulletin AB 111, setting requirements for geotechnical investigation and reporting in the foundation design of tall buildings. The city institutionalized tall building review under a set of dedicated administrative bulletins covering geotechnical and seismic peer review, with specific attention to the effects of dewatering on a project site and on the surrounding area. The lesson the record supports is not that pile foundations are unreliable, it is that heavy high-rises on soft Bay Area ground require explicit geotechnical peer review, real accounting for groundwater effects on surrounding soil, and foundation scrutiny specific to tall buildings, not just standard practice assumptions about how deep the piles need to go. Those were the gaps this building fell through on the way down. Return to the monitoring data now. The rate has slowed. The building stands. The repair is largely complete. The numbers are better than the 2021 peak, but the tower leans farther from vertical than it did the day the $100 million fix began. The foundation never reached the rock. and the clay below the pile tips is still there, still carrying load, still compressing, still settling.